But that's not. You hear it now?
Yeah, yeah, yeah.
That is. So I'm just pushing it right through and I get that solid sound.
80?
So Jamie, we took 30 different measurements and we'll get the average of those 30 measurements to calculate, you know, our best estimate of the thickness of the active layer in this area here. Yeah. On top of the permafrost, that's the one that freezes, thaws, freezes, thaws. So it's very active. There's lots of, every summer there's lots of, and fall there's lots of movement in this upper part of the ground because it freezes and thaws, freezes and thaws. Yeah. But down below it's pretty solid. But what happens with climate warming, we expect the active layer to gradually get thicker. So every summer more of the ground will warm and thaw, and what that means is that this active layer becomes thicker and thicker with climate change. Why is that important? Well, it depending on what's the type of permafrost. If there's lots of ice in the permafrost, in the permanently frozen ground, then when that ground thaws, that ice melts, and what you find is the overall ground starts to consolidate. It sort of, so the level of the ground drops. And if it doesn't drop evenly, then if you've got a structure on top of this, one corner of a house or a building might drop more than the other side, and this causes all sorts of damage to the house or to the building. So it's important to be able to know and to predict maybe how much the ground surface will change as it warms up. And so one way of knowing that is by trying to work out the amount of ice that's in the permanently frozen ground that will eventually thaw. So here, Jamie, we're trying to compare the difference in the thickness of the active layer in the wet area versus the dry area back there.
And
in the wetter areas, the active layer is much deeper and thicker because the water that sits on the surface in these wet areas, and you can see behind me here all of the ponded water in the wetland, it helps to thaw the permafrost much more because the water heats up over the summer and it thaws the frozen ground underneath. So you'd expect that under the wetlands the active layer is deeper than on the dry area where the shrubs are growing. Just let's see what we planted. So we're just taking a sample of the sediment to be able to describe how much sand and silt. Like what is this? What's the sediment made up of? Is it all is it muddy or is it sandy? So that's probably enough to do your grain size analysis. So that's the sound there, Jamie, is probably the probe hitting the top of the frozen ground. You hear it? This is sometimes when the ground gets really cold, it cracks. And I know probably around town in the middle of winter, the road, you see little cracks in the road, right? The ground gets so cold, below about minus 20 degrees, it starts to contract. Just like ice on a pond or whatever when it gets really cold. So when it cracks, what happens is in the summertime then all sorts of sand and things goes down into it, or down in the permafrost, the water that flows down into that crack in the summer freezes because the permafrost is always below zero. So it develops a little lens of ice. And the next winter when it goes to minus 20, the ground is weakest where that crack happened before. And the crack cracks again and it opens up a little bit more. And next spring, the water flows down into it, freezes. And over time, you build up this wedge, an ice wedge, a big thick ice wedge where the crack is. And so we think that this mark here in the ground might be where underneath where there might be an ice wedge. So we're looking here at some patterned ground on the surface. When the ground freezes and thaws every year, in that active layer, it churns the material around, and sometimes it makes patterns on the surface, and we call it patterned ground. And this is an example of one of these patterns that you see, and it's what we call it's a sorted circle. So it's roughly circular in shape, about maybe 6 feet across, and in the middle is the finer material, the sand and the mud. And around the outside are the big coarse boulders. So you can see all of these boulders. I'm going to walk around them for you. Around here, around here. These are all the big boulders, and the big boulders get pushed out to the outside, and the fine material gets pushed up in the middle. And it's the freezing and thawing and the freezing and thawing that does that. And if you look out across here, you'll see lots of other examples of them on the surface. If you look in this direction, for instance, the surface has been patterned ground. So Arviat was built on an old Esker. And if you look in the distance over here, behind me, you can see the community. In the old part of the community, the very earliest houses were built on the top of this ridge of gravel that's along by the water in the community. But Arviat actually has 2 Eskers. The one that goes through the community, and this one here that is farther south and intersects the airport over here. So the runway, so the Esker once run through the runway, and it's where the sewage lagoon is and areas like that. And so these Eskers or ridges of gravel were once big rivers of water coming out of the melting ice sheet. In fact, some of these Eskers would have formed in tunnels at the bottom of the ice sheet. The ice sheet might have been a kilometre thick, and all the meltwater that runs down through the ice sheet and down collects in these tunnels, and these great big floods of water would be passing out through these tunnels, and they'd be able to carry some of the big boulders and the sand that you see behind me, and they had been left here originally as ridges, and we see them all along up towards Whale Cove and Rankin Inlet. If you fly down from Rankin Inlet, you can see all of these Esker ridges coming out, flowing into Hudson Strait, and they're left over from the last glaciation. Because they have nice sand and gravel in them, they're really good for building roads and gravel pads, and so a lot of this material has been used to build Arviat and to build the runway. And so there's not much left of the original ridge, but there's lots of other places around here that we could see the ridges out towards the water reservoir and out towards Magoo's and places like that. You'll see lots of nice ridges that haven't been had the gravel taken out of them yet. This area here would have been under, we're walking on the old seabed. The seabed, that might have been, if we looked up, there might have been 150 meters of water above us. And that's almost as deep as Hudson Bay in some places. So back then this land area was just part of Hudson Bay. But over time, the sea level dropped, and it drops down to its current level, and we know that the land is still rebounding here and sea level is still falling. But as we walk along the landscape here, we're going to walk along old beaches. And these old beaches were where the sea used to be at different times in the past. And so as we walk down this slope, we're walking along the old beaches that were active thousands of years ago. Here's a nice way to track, probably. Right. Look at here. Look. These are all cracks that would have happened. Literally the ground is cracking. Sorry, Jamie. Shadows in the way. The land is very sensitive, this frozen land. So you can see, if you look out here, you can see the passage of one ATV probably along there when the ground was soft. Or over here you can see where a big bulldozer probably drove along that maybe once or twice, and the marks are in the ground forever almost, because once you compact the ground with a big weight like that, it never recovers. So you can see the marks left 50, 100 years after it has passed just once. So this is another example of patterned ground, where the frozen ground underneath causes a pattern on the surface. And in this case we call them polygons, because if you look here, what you have is a series of low sort of cracks in the ground, and they form a polygon with an area that's higher up in the middle. So Rudy, you walk over into the center of that polygon over there, you'll see. So what happens is ice wedges form in the ground, and they intersect and form, like they can be squares, or in this case maybe 4 or 5 sided. So he's standing in the middle of a high centered polygon, and we can walk around and see where the ice wedges would be. So come and follow me and we can see. So we're going to go down here, we're going to jump across this one, so there would be an ice wedge down here, and then there'll be ice wedges over here and another one over there. So it's the pattern that they form that outlines the polygon. So in this area here there's a whole series, the whole land is patterned with these, what we call these polygons. So polygon simply means many-sided. So in this case, some of these polygons have 6 sides, or maybe 5 sides. and that's why we call them. And sometimes they have a low center in them, and in this case they have a high center. So high in the middle, or sometimes it's low. Do you see those out there, Jimmy? Can you see them? This is what we're looking at. And Scylla, do you see them?
Yeah.
Yeah, so it's sort of neat. It's very different sort of surface. I don't know how we photographed them, but. So this area, the community here on the sort of towards the point, we have we've been digging around in here, and below the surface is some very fine sand and silty material. And as you can see, we dug this hole here, and it's full of water overnight. So the water table is very high. And you also have material that once you make it saturated, look at my foot here, once you make it saturated, it behaves very much like putty, and it doesn't hold very well. So we're trying to work out how we're going to take samples of this and try and work out what's the material in it. And also find out where the permafrost is. It seems to be very deep here, like over my head. Like the active layer is like 2 meters deep, so a lot more than we saw on the other side of town. And so we're interested in what sort of conditions there is in that permafrost. Is there lots of ground ice in it? So one of the things Rudy's going to do is sample the soil here above the permafrost, and we'll take samples to see what's sort of how sandy it is or how muddy it is, and also to see how much salt is in it. Because all this area was underneath the sea in the past, a lot of the material has salt from salt water, and the salt makes the ice, the permafrost, not as strong as it normally would be. So sometimes it's more difficult to build on this type of material. So we're interested in doing more work here to find out what are the conditions in the active layer and also in the permafrost below.